Welcome to this session on automating the machine learning modeling process using Oracle Machine Learning. I'm Mark Hornick, Senior Director, Oracle Machine Learning Product Management. Automation is often a key component to increase productivity and reduce cost. In today's session, we'll look at some of the challenges confronting users of machine learning, new techniques for addressing those challenges, and how we provide tools in Oracle Machine Learning to assist users. To begin, let's touch on the skills expected of data scientists. Now, there are many skills that a data scientist needs, and there isn't uniform agreement as to what those skills are. Here are just a few of 207 million pieces of advice found with this Google search. Some skills fall into the category of hard skills, such as programming, as with R or Python, data visualization, how to present data and results in a meaningful way, and data wrangling, how to manipulate data and prepare data for machine learning modeling. Others are perhaps more soft skills, like intellectual curiosity, having enough interest to pursue novel paths and not settle for the first result achieved. Communication, how to effectively convey to business decision makers complex machine learning pipelines and results in an intuitive and easily digestible way. Storytelling, which ties in with communication for making machine learning results fit the business narrative. And collaboration, working with people in a diverse set of roles and with diverse skill sets, domain experts, developers, and citizen data scientists. Now, while common threads exist across the skill sets listed here, we'll focus on the threads involving machine learning, the process techniques and algorithms associated with that. We know that data scientists and individuals with broader machine learning skills are in high demand and limited supply. Yet business solutions increasingly rely on machine learning and have rapid development cycles. In this session, we explore how we can help bridge that gap. Now, when we think about the machine learning process, the cross-industry standard process for data mining, or CRISP-DM, often comes to mind. And since we're talking about automation, it should be clear that some of these steps would be difficult to automate, if not impossible. For example, business understanding and data understanding rely on human expertise to identify business problems and the data available in the organization, as well as data from external sources. Some data preparation steps can be automated, but there's still significant domain expertise that comes into play. For example, if an algorithm requires data to be one-hot encoded, normalized, or binned prior to modeling, this is fairly straightforward to automate. Some tools even automate exploring interaction terms. However, some more interesting and useful derived variables often require domain expertise to ferret out subtle patterns and relationships. This can be as simple as mapping synonymous values like MA, Mass, and Massachusetts as the same state. A greater challenge is coming up with an effective marker for defining a churning customer that offers sufficient lead time for avoiding a defection. So, defining truly creative derived variables is not a candidate for automation, at least not today. As we'll discuss here, the modeling process is ripe for automation. Modeling is largely a well-defined and highly iterative activity, even if viewed by some as an art. However, through automation, we can increase data scientists' productivity while helping non-experts produce reasonable models. The evaluation phase requires judgments based on business understanding. For example, are the success criteria met? Will business objectives be achieved? So this isn't a good candidate for automation. We can also automate aspects of the deployment phase, making it easier to deploy, monitor, and update models for use in applications and dashboards. So let's focus on the modeling process. You have multiple algorithms to choose from. Which should be tried and which is best? So we start with one algorithm, we build a model and tune it, hopefully to improve model quality. And note that each algorithm has its own settings or hyperparameters that need adjusting. We compare each model against previous models, selecting the best model. And then we repeat this process, or pipeline, with the next algorithm. We may also have to adjust our pipeline to introduce supplemental data or transformations and try these new data sets with each algorithm and settings combination. As you can imagine, this iterative and trial and error approach is expensive, both in terms of time and compute resources. Further, it requires that you understand how to tune each type of model. So this motivates our desire to automate the modeling process. Some pain points with traditional machine learning include the need to meet rapid model development cycles and a process that is complex and highly iterative. There's a need to understand individual machine learning algorithms in enough detail to get high-quality models. Due to the wide range of algorithms, the modeling process is often time-intensive to explore the space of candidate algorithms and their corresponding hyperparameters. Broadly speaking, solutions to these pain points include introducing an efficient machine learning pipeline to address the need for rapid model development. This can be done by eliminating repetitive tasks through automation, with the goal to increase model quality and user productivity. To the extent possible, we should apply machine learning to the machine learning process itself to automatically zero in on the right algorithm and the right features, as well as the hyperparameters necessary to build high-quality models. Such capabilities help to make machine learning accessible to a broader audience, while reducing the time required to get the desired results. So this is where Oracle Labs comes into the picture, with their AutoML solution to provide an efficient machine learning pipeline. Here, an efficient machine learning pipeline is defined as one that obtains an accurate model in a short period of time. Oracle Labs provides a novel, iteration-free AutoML pipeline. This means that it eliminates the need to repeatedly iterate over various pipeline configurations, which consist of algorithm, data, and hyperparameters. In this approach, each pipeline stage makes decisions based on meta-learned proxy models that can predict candidate pipeline configuration performance before building the full final model. This way, only the best candidate pipelines are built and tuned, achieving better results in a fraction of the time, especially compared to open source AutoML tools. Many state-of-the-art AutoML optimizers are iterative and need to evaluate a large number of pipeline combinations. However, this takes a long time, making iterative pipelines impractical for large datasets with short time budgets. They can also be relatively expensive, especially if paying for cloud compute resources in some environments. The Oracle AutoML approach is radically new, however. It rapidly narrows the search space by doing one-pass preprocessing, algorithm selection, and algorithm-specific adaptive data reduction. Data reduction includes both row-wise and feature-wise dataset sampling and hyperparameter tuning. One potential drawback of this approach can be reduced accuracy, since not all pipeline configurations are tried. However, the Oracle AutoML approach minimizes such risk by meta-learning one proxy model per algorithm, and this allows more accurately predicting relative ranking between different pipeline configurations. These novel aspects of Oracle AutoML allow it to be significantly faster and, in most cases, more predictive than other state-of-the-art AutoML approaches. This slide summarizes the novel research contributions, which include an iteration-free optimizer, proxy models, adaptive data reduction, and a parallel gradient descent hyperparameter optimizer. The Oracle AutoML methodology supports both the Oracle machine learning in-database algorithms as exposed through OML4Py and the OCI data science use of select open source Python algorithms. And this points to the flexibility of the technique and provides both database and open source users with powerful machine learning modeling automation. The proxy models we referred to a moment ago are built specific to the in-database algorithms and the supported open source algorithms. So now, let's turn our attention to the components of Oracle machine learning that leverage Oracle AutoML, namely the Oracle Machine Learning AutoML UI and OML4Py AutoML. Oracle Machine Learning AutoML UI is a no-code user interface supporting automated machine learning for both data scientist productivity and non-expert user access to powerful in-database algorithms. It accelerates machine learning projects by giving quick feedback on dataset suitability for producing useful models, alleviating much of the drudgery of the machine learning process. Oracle Machine Learning AutoML UI automates model building with minimal user input. Just specify the data and the target in what's called an experiment, and the tool effectively does the rest. However, users can adjust some settings, such as the number of top models to select, the model selection metric, and even specific algorithms if they like. As we'll see shortly, running an experiment shows incremental progress monitoring and produces a leaderboard of models and their corresponding performance. With a single click, users can generate editable starter notebooks, and these notebooks contain data selection, building the selected model, including the settings used to produce that model by AutoML, and scoring and evaluation code, all in Python using OML4Py. You can build on this generated notebook to apply your own domain expertise to augment the solution. In addition, deploying models from the AutoML UI as REST endpoints to OML services takes just a few clicks. Scoring using these models is optimized for streaming and real-time applications. And like other solutions that require provisioning a VM for 24/7 availability, OML Services is included with Oracle Autonomous Database, so users pay only for the additional compute when producing actual predictions. Here's a quick overview of the experiment pipeline, adapted from what we saw earlier, which consists of 5 principal steps. With automated algorithm selection, the goal is to identify the in-database algorithms likely to achieve the highest model quality. Using meta-learning, AutoML leverages machine learning itself to help find the best algorithm faster than with exhaustive search. Adaptive sampling identifies the right sample size for training data and adjusts for unbalanced data, such as when your target has few positive cases relative to negative cases. With automated feature selection, the goal is to denoise data by eliminating features that don't add value to the model. By identifying the most predictive features and eliminating noise, model accuracy can often be significantly improved, with the side benefit of faster model building and scoring. Automated model tuning tunes algorithm hyperparameters and can significantly improve accuracy while avoiding manual or exhaustive search techniques. And finally, we have feature prediction impact, which ranks features that most influence predictions, computed in an algorithm agnostic manner, meaning that the results aren't specific to the type of algorithm used. Each final model produced per algorithm has its own feature rankings in the experiment. So let's have a quick demonstration of the OML AutoML user interface. So here we're looking at the Oracle Machine Learning user interface. We're going to start with the AutoML user interface, and so we'll click on AutoML in the quick actions. Later, we'll be looking at things such as models and notebooks as well. On this screen, we have our listing of AutoML experiments, and one that we created before, Affinity Card 360, which we're going to create now as well. So we'll call this Affinity Card 362. And we're going to select the data that we want from one of the tables that we have. So we'll search here for OML user, and we're looking for 360 for our data. And we'll choose the table customers 360. We then select what are we trying to predict, and the column called affinity card is our target. We can also optionally specify a case ID, the unique identifier for each row. And notice that the prediction type is automatically set to classification, but we may also have a regression problem solved using the AutoML UI. Now you'll notice for our table that we also have various statistics that are available on the columns that we have as predictors in our data set. So next, let's look at some additional settings. We can select the maximum models that we would like to build, and we're going to keep that at 2. We can specify the database service level. We'll choose medium so that we have multiple CPUs working on this problem. And we have various model metrics that we can select as well. And here we have balanced accuracy selected. Now there are various algorithms that we may decide that we don't want to have considered. Maybe it's important that we have transparency in our model, and so we take away a few of the algorithms that are there. Now once we're set, we can decide to start our experiment. Faster results uses fewer pipeline combinations. Better accuracy focuses on trying a broader range of possible pipeline combinations. We're going to go with faster results. So we're starting the experiment. We see that it's running, and we can click on these 3 dots here to notice our progress bar. And you see the workflow that is being processed. Algorithm selection is first, to decide which algorithms we should actually focus our attention on. Recall we asked for 2. We have then adaptive sampling, the feature selection, followed by model tuning, and finally feature prediction impact. So it selected naive Bayes and support vector machine linear as the 2 algorithms that it's going to focus on. Now we're going to let that run, but I'd like to jump over to the experiment that we have completed, and we'll just continue exploring it from here. So as you see, we have the naive Bayes completed and the support vector machine. So the first thing we can do is look at some of the model details. And we see the prediction impacts that household size and marital status and years residence are viewed as the top predictors for the naive Bayes algorithm. And we have the confusion matrix as well. That tells us how many predictions were correct and how many were incorrect and which types of errors were made. We can do the same thing for the support vector machine algorithm. Here we see that household size, education, and occupation were chosen as the most predictive variables. And similarly, we have the confusion matrix. Now notice that the accuracy for naive Bayes was a bit higher, and so that's why it's ranked first in our leaderboard. The next thing that we can do is say that we'd like to deploy our model. So we've renamed our naive Bayes model Affinity Card NB2. A model name is automatically generated, which can be somewhat cryptic, and so we're able to rename that model as we choose. So since we've already deployed our naive Bayes model, let's go through using our support vector machine linear model. So in this case, we're going to show renaming that model, and we'll call it Affinity Card SVM2. Okay, and from here, we can say we'd like to deploy that. So the name of our model is Affinity Card SVM2. We'll call it AC SVM2 for our URI. Version is 1.0. And the namespace is demo. And we'll share that model with others. So just by clicking OK, this model is now deployed to Oracle Machine Learning Services. If we go to the Models interface, we have the list of models that are available to us, but we're going to focus on our deployed models. And here you see that we have Affinity Card SVM2. It's shared, version 1.0, the demo namespace, OML user is the owner, and we see that this was just deployed on 8/23. Now, if we'd like to see the metadata for the model, here's the JSON description of the columns that are used, the output, and the labels, along with the model name. And if we click on the URI, we see the OpenAPI specification for this model. And with this, we're now ready to use it in a REST as a REST endpoint through OML services. But let's go back to our experiment. And let's generate some code for our support vector machine algorithm. We're going to create notebook. We'll call this Affinity Card 360 SVM. And now the code has been generated as a starter notebook for us to work with. So we'll open that up. This is going to start the notebook server. And now it's loading the notebook. The first thing we'll want to do is to set our interpreter binding so that we'll be able to connect to the database. And we're going to choose the medium binding again. Now, if I run our first paragraph, we'll see what is the experiment metadata that's available for this particular notebook. We have the experiment name, Affinity Card 360, the workspace, the OML user workspace. Our project is demo, and the user, of course, is OML user. The data, customers 360, that it's a classification type of model, that we're predicting the target affinity card, and we've used the support vector machine algorithm. The first thing in this notebook is to have the paragraph that imports OML, because this is going to establish a connection to the database using OML4Py. Then we get the columns that were used to produce this model, and we'll see that with the schema and the table that's used, we formulate the query, and then we sync to get a proxy object for this data in the variable build data. And here we're looking at a few of the rows of data from that table. From there, we can do additional data preparation, like separating out the predictors from the target, as is the Python convention. Next, we build the support vector machine model. We have the SVM settings that were used by AutoML, and then we can build that model. Next, we show the model details. We can have the data for scoring that we like. In this case, we'll use the predict function, and finally show some model quality metrics on that as well. So let's go back to our experiments. And this is the one that we created just recently. And we see that it too has completed. All of the steps are present. And here we see that some of the top features include year's residence, customer year of birth, occupation, and education. So that concludes our demonstration of the Oracle Machine Learning AutoML UI. So now we'll go back to the presentation. So the second component that we'll talk about that supports AutoML is Oracle Machine Learning for Python. And here we'll provide a brief introduction first. Oracle Machine Learning for Python leverages the database as a high-performance computing environment, manipulating database tables and views through Pandas data frame proxy objects with overloaded functionality that's translated to SQL transparently behind the scenes. You can invoke in-database scalable machine learning algorithms through a natural Python interface, as we just saw with the generated notebook. And on Autonomous Database, you can take advantage of optimizations such as autoscale. Users can create user-defined Python functions managed as scripts in the database. And Python objects can also be stored in the database, as opposed to being managed in flat files. These user-defined functions can be run in database environment-spawned Python engines through the use of multiple Python engines Users benefit from automated data parallel or task parallel invocation from Python, REST, and SQL APIs. Results can contain both structured results, such as data frames, and image results, for example, as produced using matplotlib. Next is model explainability, or MLX, which provides model-agnostic identification of important features as they impact model predictions. And OML4Py supports automated machine learning, or AutoML, which we'll dive into a little bit more now. So in OML4Py, users have access to functions supporting 3 key AutoML steps: automated algorithm selection, feature selection, and model tuning. And this is aligned with what we discussed earlier. There are also functions for model explainability, or MLX, as well as a model selection capability. Let's have a quick demonstration of OML4Py AutoML. So now we're back to the Oracle Machine Learning user interface with Autonomous Database, and we're going to click on the Notebooks quick action. And this takes us back to the set of notebooks we said earlier, but this time we're going to open up the OML4Py AutoML notebook. So this is the OML4Py AutoML notebook that we just opened. And you see the markdown, which gives an introduction to OML4Py, as well as the features of this notebook that we'll be talking about, such as automated algorithm selection, feature selection, and model tuning. The first thing that we do is to import libraries and set display options. So in this case, we import pandas, OML, and also the AutoML subcomponent of OML itself. Next, we're going to create data sets as pandas data frames and load this into Oracle database. So in this case, we're using the wine data set from scikit-learn. We have the concatenation of the predictors and the target, and we're using the function OML create with this new data frame, and we're creating a table called wine. And then we'll print the shape of that data set as well as the data types that are associated with that. So now this just took the data from our Python environment and loaded it into Autonomous Database. And we can also look at some of the data in this table as well, getting the first 20 rows from the proxy object, wine. Next, we're going to look at automated machine learning algorithm selection. Now we can do this both for classification and regression. We're just really going to talk about the classification side, and occasionally I'll point out a few things on the regression side as well. The first thing that we'll do is to separate the predictors from the target. On the classification side, we're using the target column called target. And on the regression side, we're going to predict proline. The next thing we do is algorithm selection. Here we define the mining function as classification. We can define what score metric that we would like and whether or not we'd like parallelism to be used to support that on the back end. Next, we invoke select using our data set and indicate how many of the top algorithms we would like to be selected. And here we see what the result is. SVM Gaussian was chosen as the best with a 98% accuracy, followed by SVM linear and other algorithms as well. Next is automated feature selection. And in this case, recall that we're looking to find which features are most relevant for the algorithm that was selected above. Here again, we create a feature selection object indicating its classification. The score metric is accuracy, and that we have interest in using parallelism. We also wish to reduce the set of columns. So we invoke the reduce function. The algorithm that we chose up above is the support vector machine algorithm. And we provide the data, our predictors and target. With this, we see that the number of columns has been reduced from 13 down to 9. In contrast, if we look at the regression side, we see that the 13 predictors were reduced to 6. Next is automated model tuning. We specify a model tuning object, saying classification, and we want some parallelism. Specify the algorithm, the reduced set of predictors that we determined up above, and our target. And from this, we see the support vector machine algorithm with these hyperparameters selected. Now, it's possible that a data scientist may have a different set of search space parameters in mind or wants to work with a specific algorithm. In this case, we give the ability to specify the search space. Here we're looking at random forest and saying, well, we have some specific range of values we would like for the sampling ratio, for the number of trees, for the impurity metric, what we'd like tried, both entropy and Gini. Then we'll invoke model tuning explicitly, providing our algorithm and the score metric we want, in this case, F1 macro. And then we'll invoke tune, providing the algorithm RF for random forest, the predictors that we have on the original data set, and the param space that we would like. And from there, we see that we have the tuned model as well. And on the regression side, we opted to do something similar, but for the neural network algorithm. And here you see options for the regularizer, activations, hidden layers, and nodes. And so you can control a great deal of this if you like. Lastly, we'll talk about automated model selection. And in this case, this is combining both the algorithm selection and the hyperparameter tuning in a single step. So if you want a single step to accomplish a model build, you can identify that as well. Here we simply say select, providing the original data. We want the top model to be tuned, and we use cross-validation, and we can indicate that we'd like cross-validation with 2 folds. And that completes this demonstration of Oracle Machine Learning for Python AutoML. When it comes to modeling and deployment, there are multiple ways to produce and consume models using Oracle Machine Learning. Here, with OML AutoML UI, once an experiment has produced the desired results, one or more of these models can be deployed to OML services for immediate use by custom enterprise applications, including those based on Oracle Apex, using REST endpoints. And as we just discussed, users can generate a notebook for a selected model and customize the generated Python code, then run the notebook to build a model. This resulting in-database model can be exported and deployed to OML services for use by applications, or that same model can be used immediately by applications from SQL. Of course, models produced by the AutoML UI can be used directly in SQL queries as well for scoring by applications. And those same models are available within Oracle Analytics Cloud, leveraging OAC's integration with OML for scoring and visualization. Using OML notebooks, users can leverage OML4Py's AutoML to build models programmatically, or use the individual algorithm modeling API to build and evaluate models manually. OML notebooks provide similar options for deployment through OML services and for use in Oracle Analytics Cloud. Note that models produced in the cloud on Autonomous Database can be exported and deployed in other Autonomous databases as well as on-premises Oracle databases. Similarly, you can build models on-premises and deploy them to Autonomous Database. So OML offers flexibility to operate on the cloud and on-premises. To wrap up our discussion, here's a quick summary of the Oracle Machine Learning family of products that supports data science projects. Oracle Machine Learning provides interfaces for 3 popular languages, SQL, R, and Python. OML for SQL exists in all database versions and platforms. OML for R is currently supported for on-premises database and DBCS. And OML4Py is supported on autonomous database and on-premises 21C Oracle database. For interaction with autonomous database, we provide OML notebooks based on Apache Zeppelin with SQL, PL/SQL, Python, and Markdown interpreters. The same notebook can contain SQL and Python paragraphs, allowing users to choose the most effective language for the task. Users can version notebooks and schedule notebooks to run. Oracle Data Miner is a SQL developer extension that enables users to create, schedule, and deploy analytical workflows through a drag-and-drop user interface that's compatible with on-premises and database cloud service databases. Oracle Machine Learning for Spark provides machine learning in the big data environment, such as Big Data Service, with native scalable algorithms, as well as Spark MLlib algorithms included in the same framework. And as we discussed earlier, we have the Oracle Machine Learning AutoML UI. That's a no-code user interface that automates the model building selection and deployment process. And lastly is OML Services, which is a RESTful service for model deployment and management, along with cognitive text analytics. Users can deploy a model from the AutoML UI directly to OML Services in just a few clicks, as we demonstrated. So for more information on Oracle Machine Learning and Autonomous Database, check out these resources. The OML4Py Live Lab allows you to quickly spin up a free autonomous database and work through multiple notebooks, introducing you to the range of OML4Py capabilities, including AutoML. In this same environment, you can also try the AutoML UI to create and run experiments. Also check out our Oracle Machine Learning office hours, where we conduct webinars on all things Oracle Machine Learning. And there's a rich library of past sessions that you can watch. As we noted earlier, Oracle Machine Learning is integrated with Oracle Analytics Cloud, and there are a wide range of analytics examples that you can draw upon there. Below, you see a few additional resources specific to the OML4Py, OML AutoML UI, and OML services. Thank you for joining today's session. You can follow me on Twitter, connect on LinkedIn, and join our machine learning LinkedIn group as well.